So when we started talking about recursive definition, we say that they're useful for proving properties of sets. And in this lecture, we will see some examples of what kind of things you could prove about sets if you have their recursive definitions. So just a quick reminder, you've seen it before. So you could recursively define, for example, a set of binary strings by saying that empty string is in the set, and if you take a string from the set and append a 0 at the end, you get something in a set, append 1 at the end, you get something in a set, and there is nothing else in the set. So here's what we could do with this. Suppose we want to prove some property of, a set of strings. Let f of x, where x would be, say in this case, strings, be a predicate with a domain that's not just our set, but usually something bigger. For example, we may be talking about not just binary string, but a subset of binary string that has a certain property, like all strings that start with 0 and end with 1. And now suppose that this property of strings looks like this. It's true for all strings in the basis, and every time you take strings that have the property and you apply the recursion rules to them, you get something that also has a property. If you could prove those two things, then you could show that every element in your recursively defined set satisfies the property. So here is an example. Let's define a set of numbers like this. We start with putting 3 in the set, that's our basis, and every time we have two strings in our set, their sum is also in the set. So what kind of strings are we going to get? At the beginning we have just 3, so x and y would be 3, we take their sum, we get a 6. Now we have 3 and 6 in the set, so we could get 9 two different ways, and we could get 12. So now we have 3, 6, 9, and 12, and we can keep going with those. Okay, so let's prove something about the elements of this set. And this is something that kind of probably looks obvious to you because of the construction. We will show by structural induction that all numbers in this set are divisible by 3. So let's do it. The base case is 3, and, well, 3 is divisible by 3. The recursive step, let's say x and y are in the set S, then they are both divisible by 3. X is equal to 3 times z for some z, and y is equal to 3 times u for some u, where z and u are natural numbers, so integers. In this case, natural numbers. Now let's apply the recursion to x and y. We take x and y and we take their sum, and we end up with a number x plus y. What does it look like? It's equal to 3z plus 3u, because x was equal to 3z and y was equal to 3u. So we got a number of the form 3 times something, 3 times z plus u, which means we got a number that's divisible by 3. And here we are done. We've shown that every number in our set that we constructed with this recursive definition is divisible by 3. Okay, so now let's look at something a bit more complicated, but something that you're going to see a lot in your data structures and algorithms classes. Just a reminder that we had the recursive definition of a tree, or at least computer science notion of a tree, as an undirected graph without cycles. So you have vertices, you have lines, edges connecting those vertices, and in this case we assume that every line goes both ways, so we don't put arrows at the ends. And something is a tree if there is no cycle, that is, for any, you could think about it this way, for any two vertices there is only one kind of short way to get from that vertex to the other one, you cannot go two different ways, you cannot go around in circles. And our recursive definition was like this. We started with a single vertex, and at every step of the recursion, we can take another vertex that's not in a tree yet and connect it to some vertex in our tree, like this. Okay, so let's make more complicated definition. So a rooted tree is a tree that has a special designated vertex that's called a root. So think about family trees. In a family tree, you have grandparents, you have parents, you have children, and you kind of think about them as being at different levels of hierarchy, so to say. So grandparents are before parents, parents are before children, before grandchildren, and so on and so forth. So here, kind of the oldest member of the family would be the root of the family tree, the person from whom it all started. And if every person has two children, then we consider the tree binary. That is, your vertex on the very top, the root, has two children. Each children of the root has either can have at most two children, and so on. And by the way, if it cannot have one child but it either has two or none, then we call it a full rooted binary tree. Okay, that's a bit of a mouthful, but hopefully you see what all of those words mean. Rooted dedicated vertex root, the matriarch of the family. Binary, everybody has two children. Binary full means everybody has either two children or no children. And here's the recursive definition now of those rooted full binary trees. So again, we start with a single vertex. That vertex is a root of its own tree. Single person who starts the family, starts the dynasty. And if we have two full rooted binary trees, we can make them into one by getting another vertex that's not in either of those two trees, calling it the new root, and making roots of those trees T1 and T2 its children. So we get a new root, and the two binary trees will be its children. So think about your family and somebody else's family discovering that they have a common great-great-great-grandparent. Okay, so when we define trees this way, we could talk about layers of the tree, but in particular, we could talk about the height of the tree. A height is the maximum distance, the maximum number of edges from any node in the tree, from any vertex to the root. A root is distance 0 from itself. A child of a root is distance 1. A child of a root is distance 2. So think about the height of the tree as the number of generations, saying the matriarch of a dynasty. And here is what we are going to prove, and this is going to be very useful in a lot of your algorithm and data structures, is that if we have a full binary tree and its number of vertices is n of t, and its height is h of t, then it must be the case that the number of vertices in this tree is 2 to its height plus 1 minus 1 at most. It can be fewer, it cannot be more than that. Or another way to say it is if you have a binary tree with n of t vertices, and it's a full binary tree, then its height cannot be more than log of the number of vertices. Where it comes handy is when you start talking about parallel programming, when you have a program that calls itself twice in parallel and its copies call themselves twice in parallel and so on and so forth. And there is some piece of code that's doing this calling of the program, and say this piece of code overall executes n times. Well, you know that overall this program has to take time at least log of the number of times this piece of code executed, even if everything possible is checked in parallel, because if a program calls itself, it cannot execute what it's calling in parallel with it being called. Okay, now let's go ahead and prove that claim that the number of nodes in a tree, the number of vertices, is at most 2 to the height of the tree plus 1, and the whole thing minus 1. And the proof will be again by structural induction. The basis of the recursive definition of rooted full binary trees was a tree with a single vertex. The tree had n equal 1, well, it had a single vertex, and the height was 0 because there is only one vertex which is distance 0 from itself. So if we plug 0 for h of t and 1 for n of t, 2 to the 0 plus 1, that will be 2 to the 1, that's 2. 2 minus 1 is 1, which is greater than or equal to the number of nodes, 1. Good, so now let's do the recursion. Suppose T1 and T2 are rooted full binary trees, for which we can apply induction hypothesis, for which we assume that their number of nodes is at most 2 to the height plus 1 minus 1. And now we build a new tree, let's call it T, by taking a vertex V, which is a new vertex, it's not in T1 and not in T2, and hanging T1 and T2 off from the vertex V, which will be our new root. So how many nodes are in the new tree? Well, we have all the nodes of T1 plus all the nodes of T2 plus the vertex V, n of T1 plus n of T2 plus 1. So what is the height of our new tree? Well, to get to the new vertex V, every vertex of T1 or T2 would need to make one more step that it needed to make to get to the root of respectively T1 or T2. T1 and T2 may be different height, so since the height of the tree is a maximum over all distances from a vertex to the root, we will take the height of the new tree to be 1 plus maximum of the height of T1 plus height of T2. Okay? So now we know how to recursively express number of nodes of T in terms of number of nodes of T1 and T2, and the height of T in terms of height of T1 and height of T2. And now everything is ready to apply the inductive hypothesis. That is to refer to the fact that we know that the relation between number of nodes in T1 and its height and number of nodes in T2 and its height. We'll do it on the next page. So again, n number of nodes in T is the number in T1 plus number of T2 plus 1 for that new root node V, which is 1 plus 2 to the height of T1 plus 1 minus 1 by inductive hypothesis, plus the same thing for T2. And now, as before, we could take a maximum. So remember, we said that the height of T is 1 plus maximum height of T1 and height of T2. So instead of talking about height of T1, height of T2, we could take a maximum of the two, or we could just take, rather than summing 2 to the h of t1 and h of t, 2 to the h of t1 plus 1 and 2 to the h of t2 plus 1, we could say it's at most 2 times the maximum of those two. And also it will be 1 minus 1 minus 1, so in overall we subtract 1. So now finally we see that the resulting expression is 2 times 2 to the maximum of the two heights plus 1, and we know that it's h of t, so we can replace it with h of t. We do have the minus 1 where it's supposed to be, and the 2 in front of the expression, 2 times the maximum, 2 times 2 to the h of t, that now can be brought up in the exponent and it becomes plus 1. Remember that 2 times 2 to the k is equal to 2 to the k plus 1. And that completes our proof. So we just shown that the number of vertices in a full binary tree is bounded by 2 to the height of the tree plus 1 minus 1, which will come really handy when you start talking about efficient ways of solving various problems, of sorting, of making priority queues, and so on and so forth. Okay, let's finish with the puzzle for next time. Yet another chocolate puzzle. So in this case, suppose you have a piece of chocolate with squares on it, and now the puzzle are the following. How many squares are in this piece? If you are tempted to just count little squares and say, oh yeah, it is 16, well, it's more than that, because the whole thing is a square. And say first, second pieces, little pieces in the first and the second row, they form another square, and so on and so forth. So for example, this will be a square, and this will be another square, and of course something like this is a square, and so the whole thing is a square. If you start counting like this, how many squares will you have? So think about it for next time.